A very good afternoon to one and all present here. It is my honor to introduce our next speaker for the day, Professor Balasubramanian. Professor Balasubramanian is a leading number theorist and is well known for his study in the field of Riemann zeta functions. Professor Balasubramanian has done his PhD from TFI Mumbai and was the director of Institute of Mathematical Sciences in Chennai. He is also the president of Cryptology Research Society in India. Professor Balasubramanian is the recipient of a number of awards and recognitions, which includes the prestigious Padma Shri Award and the French government's National Order of Merit for furthering the Indo-French connections in the study of mathematics. The professor will now be giving us a talk on the Selberg's approximation to the twin prime problem.
Thanks for the organizers, in particular Manisha, for this opportunity to be able to be here and present some works on the Selberg's approximation to twin prime problem, and probably I think the title itself probably needs a little lot of explanations. Okay. In the morning when Professor Surya Ramana was talking, he said that most of the problems in number theory, one either uses the so-called analytic method, which essentially means you study something called a Riemann zeta function, the analytic properties of the Riemann zeta function, use some complex analysis and so on and so forth. And the other method is combinatorics. And the combinatorics itself falls into two parts. One, what is called additive combinatorics, that's the type of one which he was talking about, and sieve methods, which is the one which I want to talk about. Okay. And the sieve methods, I mean, most of the number theoretic problems are essentially solved by sieve methods, and in fact, around 4 years back, when you saw probably in the newspapers that there was a work of Menard and others related to twin prime problems and things like that, they would have talked again essentially about the large sieve and various sieves. Okay, therefore, what is sieve methods? The sieve method essentially starts with the Eratosthenes. And the Eratosthenes sieve is the following. I am interested in the number of primes. I am interested in counting the number of primes up to, let us say, 10,000. Or at least I want to find out a table of primes up to 10,000. And how do you find out a table of primes up to 10,000? Then what you do is you write all the numbers from 1 to 10,000. And then you erase all multiples of 2, you strike down all multiples of 2, and then you strike down all multiples of 3, then all multiples of 5, all multiples of 7. Okay? Therefore, when you erase this, the 3 is the first number that is allowed, and therefore that use, then 5 is the number, and then you erase the multiples of 5. If you do that, till what stage we should go? We should go up to 100. And when you go up to 100 and then you stop there, then whatever that is left are primes between 100 and 10,000. Okay? That is exactly the Eratosthenes sieve. Now the question which you would like to know, there is one thing, that is around 2000 years old. But then around 16th century people were interested in counting the number of primes. How many primes are there up to a given number n? And that was a very interesting question, and there were various conjectures that were made about the number of primes up to n, and the important conjecture is the so-called prime number theorem. That is, the number of primes up to n, which is pi n, is around n over log n. And this log n is not the computer scientist's log n, this log n is a mathematician's log n, which means that it is to the base e and not to the base 2. And now one would have naturally thought that now that Eratosthenes has developed a method to really write down the primes, cannot this method be really used to count the number of primes? Good. Which means that you take all the numbers, throw away the multiples of 2, throw away the multiples of 3, throw away the multiples of 5, see how many numbers you have thrown away, correct? But on the other hand, you have overthrown, because the number 6 has been thrown twice. When you are throwing multiples of 2, you are throwing it away, you are throwing multiples of 3, you are throwing it away, and therefore the numbers like 6 has to be again added. Therefore all the take a prime and all its multiples you throw, and then take two primes, P1 and P2, 2 into 3, 6, and those multiples you add because they have been already thrown once. But then the numbers like a 30, okay, which is 2 into 3 into 5. Originally when you throw the 2, you threw it, and 3 also threw it, 5 also you threw it, and therefore 3 times you have thrown it. And on the other hand, when you are counting 6, you have added it. When you are counting 10, you have added it. And you are counting 15, you have added it. 3 times you have added it. But this 30 is not really a prime. It has to be thrown away. Therefore throw it away. Good. Therefore what you end up with is all multiples of primes you throw away. All multiples of 2 primes, P1, P2 type thing, you again include. Then all P1, P2, P3 you throw away. All P1, P2, P3, P4 you include. If you do that, you should get exactly the primes. Good. And this is what most of you would have studied in your combinatorics as inclusion exclusion principle. That's exactly what it says. Therefore, the question naturally arises whether can we not do this inclusion exclusion principle. If you do the inclusion exclusion principle, then what you is supposed to end up with, if you are starting with the events which are independent, then 1 minus the probability of the event happening. Therefore, what you would expect is really pi of n to be n into product of 1 minus 1 over p, because the event that it is divisible by p happens with the probability 1 over p. Therefore, it doesn't happen with the, therefore it's not divisible by p, happens with the probability 1 minus 1 over p. And the events are independent. Divisible by 2, divisible by 3, divisible by 5, etc. are independent. And since they are independent, therefore you should be left with these numbers. Is it okay? This is what you would expect. Good. But unfortunately, it does not happen. This does not happen for the simple reason that if you are fixing an n, let's say n is 100, then the probability that 2 divides is half 1 over 2, because there are 50 numbers which are even numbers, but the probability is divisible by 3 is not 1 over 3, it is only 33 by 100, because there are only 33 elements which are divisible by 3 out of the 100. Okay? Therefore, the probability of divisibility by 2 is half, the probability of divisibility by 3 is 33 by 100. The probability of divisibility by 6 is again exactly 16 by 100, which is not equal to the probability of divisible by 2 into the probability of divisible by 3, which means that the events are not really independent. Okay? They are independent with a small error margin. Since they are independent with a small error margin, if you are not taking too many events, you can still survive. But if it takes too many events, then this error will blow up. Okay? And that is exactly what is happening. Therefore, whatever I said, let me write in a number theoretic way. Therefore, A is a set of integers, P is a set of primes, Z is a parameter, and I want to sieve out primes up to Z, which means once I sieve out by primes up to Z, I will be left with only numbers which are co-prime to all the primes up to Z, which have nothing in common with all the primes up to Z. That is one example. The other example is I want to count twin primes. What are twin primes? Two consecutive odd numbers, if they are primes, they are called twin primes. Okay, 3 and 5 are twin primes because 3 and 5 are odd consecutive numbers. 5 and 7 are twin primes. 11 and 13 are twin primes. 17 and 19 are twin primes. Okay, therefore 29, 31 are twin primes. Therefore, we have a lot of twin primes. The question naturally is, this is a question which dates back around 2000 years back, saying whether there are infinitely many such pairs of twin primes. Okay? And then under even probability considerations, people were even able to make a certain asymptotic formula for the number of twin primes. How many twin primes would exist, and so on and so forth. And that also can be done. You start with the set n into n plus 2, and then you say that n into n plus 2 should be, you remove all prime. If n into n plus 2 is a multiple of a small prime, then you remove that term. Therefore, n into n plus 2 will not be a multiple of a small number, which essentially means this n also has to be a prime and n plus 2 also has to be a prime. That's exactly what you do in Phillips primes. And now I was talking about the inclusion-exclusion principles. One of the easiest way to actually get this inclusion-exclusion principle is to use what is called the Mobius function. Okay? Because now let's see what did we do. We removed the primes. Therefore, when I removed the multiple of primes, I subtracted. When for P1, P2 I added. For P1, P2, P3 I subtracted. P1, P2, P3, P4 I added. But P1 square, for example, I never did anything. Okay, P1 square, P3 I never did anything. Okay, therefore I just introduce a number like that. For P1 it is plus 1. For P1, P2 it is minus 1. Sorry, other way. P1 it is minus 1. P1, P2 it is plus 1. P1, P2, P3 it is minus 1. P1, P2, P4 it is plus 1. If it is P1 square, it is 0. P1 square times Q1, it is 0. Because these are the numbers which are not, these multiples are not removed in the Eratosthenes receive. Eratosthenes receive, the only multiples which are removed are multiples of P1, multiples of P1, P2, multiples of P1, P2, P3, P1, P2, P3, P4, etc. Correct? And therefore that's exactly, for P1 I put minus 1, for P1, P2 plus 1, P1, P3, P1, P2, P3 minus 1 and so on and so forth. Okay, this one I will come back. And therefore, the summation d dividing A, d dividing P is at mu d. Well, that's an important theorem. This particular number, yeah, this is one number which I need, where I have written. This is an important thing. Summation d dividing n mu d is exactly 1 if n equal to 1 and 0 otherwise. Therefore, this is in some sense the function which determines 1. In other words, if I now take any n, let us say 7, and d dividing n mu d, therefore 7 I take all the divisors of 7, for each one I compute the value of mu and add, then I will get 0, because for 7 there are only 2 divisors, 1 and 7, mu of 1 is 1, mu of 7 is minus 1, therefore that is 0. And that happens for everything, even for 6, because 6 there are 4 divisors, 1, 2, 3 and 6. Mu of 1 is 1, mu of 2 is minus 1, mu of 3 is minus 1, mu of 6 is plus 1, because 6 looks like a P1, P2, and that addition is 0. Therefore, you can always get the number 1 if the n is 1, 0 otherwise. And that is what exactly I write here, the first line, which is exactly the inclusion-exclusion principle. Therefore, let me explain what that means. I now take the a given number A, and P of Z. P of Z is all the primes up to Z. Therefore, I take the A, I take the P of Z, and I take the divisors of A and P of Z, and I do it for mu for each one of them and add. Now, when you take the divisors of D and P of Z, okay, therefore, I want a number which divides D as well as P of Z. A number D which divides A as well as P of Z. But to say that this D divides A as well as P of Z is equivalent to saying that D divides the GCD of A and P of Z. And since the D divides the GCD of A and P of Z, and therefore if I look at the divisors D of the GCD of A and P of Z, compute the mu of D and add, then this number will be 1 only if the GCD of A and P of Z is 1, and if it is anything else, it will be 0. Therefore, this counts precisely when A is co-prime to PZ. That's exactly what it is. Therefore, summation over A, D dividing PZ, mu of D. And then I do some simplification. We will forget it. And the simplification essentially gives you mu of D into A of D, namely the multiples of D. The number of multiples of D up to x is the integral part of x over D. Therefore, this modulus of this A of D is precisely the integral part of A over D, x over D. Now, in the morning again, Surya Ramana was explaining, in most of the time, replacing the integral sign by the number itself will not lead to any error. But unfortunately, in our case, it will lead to an error because the summation has too many terms. Okay? P of z is all primes up to z, and you are counting how many divisors are there. The number of divisors is something like a 2 power z. Therefore, you have 2 power z terms. Since you have 2 power z terms, and in each one of them, you are removing the integral part by the number, and therefore each one introduces only a bounded error. But even though each one introduces a bounded error, the number of terms is too many, 2 power z. Therefore, it will introduce an error which is something like a 2 power z. That's exactly what you are getting. When you do all those things, yes, x into product 1 minus 1 over p, which is precisely what you would expect, because you are throwing the multiples of p for each p, and the probability that a number is divisible by p is 1 over p. Therefore, the probability that a number is not divisible by p is 1 minus 1 over p, and therefore, by probability consideration, the main term should be 1 minus 1 over p, but there will be an error which is O of 2%. And this is exactly what I said. If there are z events, then you end up with an error 2 power z simply because the probability of divisibility by 2 and the probability of divisibility by 3 are not independent events. The probability of divisibility by 6 is not exactly equal to the probability of divisibility by 2 and probability of divisibility by 3. And that error, which is a bounded error though, the bounded error happens for every event, and therefore you get a 2 power z. That essentially means, therefore you see, you have a main term which is something like an x times e power minus gamma divided by log z, because it is known that the product 1 minus 1 over p is something like a e power minus z by log z. But there is an error term which is 2 power z, and therefore you can choose only z to be even smaller than the main term. If the error term exceeds the main term, there is nothing which you can do, which essentially means you are forced to prove, take z to be something like a log x by 2. Which means the error transfer receive is not useful for you to sieve out all primes up to root x, which is ideally what you want. Maybe you can sieve out up to log x by 2 primes. And then it will give you something like an x over log z. Okay, which gives you something like an x over log x, because that you are taking to be around log x, which is of course an upper bound. And now what we want to do is to slightly something else, which was an idea devised by Brun, Viggo Brun. Viggo Brun's idea was essentially that he has to keep the total number of terms in control. So he has to keep the total number of terms in control. Then if he removes that integral part of the number, by the number itself it gives a bounded error. But since the total number of terms is in control, still the error can be controlled. And how do we do that? Again, we go back to our inclusion exclusion principles. We started with the whole L, and then we removed those multiples of P. Okay, let's write multiples of P. Then we added multiples of P1, P2. Then we removed multiples of P1, P2, P3. Then added it, and so on and so forth. That is exactly what we did. Okay. Therefore, the total number. Okay. Therefore, if there are totally R primes which you are looking at, okay, then the first sum will have R elements, because R primes you are looking at. The second sum will be RC2 elements, because you are choosing 2 of them. Then you are having RC3 elements, because you are choosing 3 of them, and you are adding all of them, and 1 plus RC1 plus RC2 plus RC3 plus etc. gives you the 2 power R, which is precisely what we got. Therefore, the number of terms is something like a 2 power R, and it is 2 bits. But on the other hand, something interesting happening here. When you take the n minus, I throw away only the multiples of p, okay, then I get something which is not some arbitrary thing. What I am getting is in fact a lower bound for the number of primes, okay, because some of them have been thrown 2 times, but that's okay. Everything which should be thrown has been thrown. Some of them may be 2 times, and therefore what I get is a lower bound. Now when I add 3 terms, I get an upper bound, and then I subtract, I get a lower bound. Therefore alternatively I seem to be getting an upper bound and lower bound and upper bound and lower bound. And once I get an alternatively an upper bound and lower bound, etc., and suppose I decide somewhere to stop, then of course I won't get an asymptotic formula. I will get an upper bound or lower bound. But the fact that I have stopped somewhere would mean that the number of terms involved is not too much. Number of terms involved is too little, and once the number of terms is involved is too little, the error term is too small, and therefore I can probably still manage. Okay? Not a very, it turned out to be a very profound idea. Nobody thought that, just you stop somewhere, you get an upper bound or a lower bound, and then you can do that. And that's exactly what we are going to do. That is a Broun sieve. In the Broun sieve, I can even tell you, okay, therefore, Broun sieve, what happens essentially is when you do that, the fact that you can actually sieve out primes, not up to log x by 2, but more or less up to a power of x. Therefore, let me even just write it. Therefore, you can sieve your z, you can even take up to a power of x. By really stopping at an appropriate stage. You can stop at an appropriate stage and you can sieve out up to a power of x. And if you do that, therefore which you mean, if you do this inclusion exclusion up to a certain stage, taking primes up to power of x, you actually get the number of primes is n times product p not exceeding z 1 minus 1 over p, which is what you would expect. And this is something, as I told you, is e power minus gamma divided by logarithm of z. N is a power of z is a power of n. Therefore, you get n over log n. And of course, there will be a slight problem. You get n log n by log n. Let's say. Therefore, you essentially get your prime number theorem. You essentially get your prime number theorem by Broun sieve. Okay, but not as an asymptotic formula, as an upper bound. But again, upper bound and lower bound, you can get both. Anyway, depending upon where you stop. If you stop at a certain stage, then you get an upper bound, and then you stop at the next stage, you get a lower bound. Okay? Therefore, you get that, and that is the idea of Broun sieve. Therefore, without using any analysis, no zeta function, he was able to prove essentially the prime number theorem. The more important thing is regarding the other problem. The other problem is that I take n into n plus 2. Okay. In other words, let me say what I am doing. In Eratosthenes sieve, I take the n, and if n is a multiple of p, I throw it away, otherwise I don't throw it away. The same thing I can rewrite slightly differently. If n is equal to 0 mod p, I throw it away. If n is not 0 modulo p, I do not throw it away. Because that's the same thing, whether I say n is a multiple of p or n equal to 0 mod p. Therefore, n equal to 0 mod p, I throw it away. And if n is not 0 mod p, I don't throw it away. And therefore, I take a prime 5, and then I look at all the n's. Whichever n is 0 mod 5, I throw away the n, and otherwise not. But for twin prime, I want n to be a prime and n plus 2 be a prime, which means I take an n, check whether it is 0 mod 5. If it is 0 mod 5, I throw it away. If it is minus 2 modulo 5 also, I throw it away. Otherwise, I don't throw it away. Okay, therefore, if n is 0 mod p, I throw it away. If it is minus 2 mod p, I throw it away. Otherwise, I don't throw it away. This I do for every prime. P is equal to 3, 5, 7, and 11, 13 for every prime. If I take a number and 0 modulo of p, I throw it away. If it is minus 2 modulo p, I throw it away. Otherwise, I don't throw it away. Therefore, for everything, I am throwing 2 residue classes modulo p. instead of one residue class modulo p which I was throwing, I am now throwing two residue classes modulo p. And in fact, the Bruns idea works as long as you don't throw away too many residue classes. So 10 residue classes, 15 residue classes, if you throw away, it still works. If you do it much more than this gives an inefficient results. But for a small number of residue classes, it works. And therefore, this Bruns sieve is what is called one of the small sieve. Yes? No, I want n to be a prime. I want n plus 2 to be a prime. Correct? How do I ensure n is a prime and n plus 2 is a prime? N should not have a small prime factor. N plus 2 also should not have a small prime factor. N plus 2 I want to be a prime. Okay? How do I ensure n plus 2 does not have a small prime factor? If n plus 2 has a small prime factor, that n I throw away. I take the elements 1, 2, 3, etc. up to 1000. 10,000. And I want to count twin primes, which means I want to count that number n for which n is a prime or n plus 2 is a prime. Correct? Therefore, now you see the number 17 I will not be throwing away. No way. Because 17 is a prime and 19 is also a prime. And now the number, let us say 35, I have to throw away. Therefore, how do I throw away this 35? Now, you see, when I am looking at the multiples of 5, this 35 is a multiple of 5, and therefore I have to throw away. Correct? Which means, when I am looking at all elements which are 0 mod 5, I throw away the 35. Correct? Good. And now let us look at the number 79. The 79 also I want to throw away. 79 I want to throw away because 79 is a prime, but 81 is not a prime. Since 79 is a prime, but 81 is not a prime, the 79 I have to throw away. Okay? Instead of 81, let's take some other nice number. Let's say 103 I want to throw away. 103 I want to throw away because 103 may be a prime, but on the other hand 105 is not a prime. Therefore, 103 I have to throw away. Okay, how do I throw away this 103? That is because of a certain prime factor of 105, namely 5. When I am looking at 5, I should throw the 103. Therefore, I just check whether this 103 is minus 2 modulo 5. This 103 is minus 2 modulo 5, and therefore 103 plus 2 will be divisible by 5. Using that, because of that, I throw away the 103. Okay? Therefore, I choose a number. If it is 0 mod p, I throw it away. If it is minus 2 modulo p, I throw it away. Otherwise, I keep it.
So, what were 101 and 103?
Sorry?
101 and 103. So, I want to keep that because that's a twin prime, right?
I want to keep only twin primes.
So, 101 and 103.
Oh, no, wait. Therefore, let's see. Therefore, I am not looking at this as a pairs. I am saying that n is a good number if n is a prime and n plus 2 is also a prime. Let's put this way. Therefore, I want to keep only the good numbers. Therefore, the 105 doesn't come into the consideration. Only 103. I want to keep only the good numbers. 103 is a bad number. If that number should be a prime, that plus 2 should be a prime. If it satisfies both the conditions, it's a good number which I want to keep. Therefore, how do I check whether a certain number is a good number? If that number is a 0 modulo p, it's a bad number. If it is minus 2 modulo p, also it's a bad number because of that. And the only numbers which will be left with us are both 0 modulo p, not 0 modulo p, not minus 2 modulo p, which essentially means it will be a good number. Okay? And now this I can do. But now for every number I am throwing 2 residue classes. Therefore, the probability of a number being good number with respect to one given prime is only 1 minus 2 over p now. Because there are 2 possibilities that the number can be eliminated. The number remaining has a possibility only 1 minus 2 over p. And therefore, if I do these things, and how many numbers will be left, and by the natural probability consideration, the numbers that will be left are now 1 minus 2 over p. Okay? And now 1 minus 2 over p, again by the same argument, is practically 1 minus 1 over p whole square. Okay, there's not much difference. And product 1 minus 1 over p we have already seen to be e power minus gamma by log z. And our product 1 minus 2 over p should be something like a constant by log z whole square. And if I followed a transfer receive and check my z to be log x, nothing would happen. But the fact that I can now choose my z to be x power 1/4 means that this number is smaller than constant times n over log square n. Therefore, the number of good numbers, which is the same as saying that the number of twin primes is at most constant times n over log square n. That was a great result of Vigo Brown. Now the question is, he stated it in a slightly different way. That is a little interesting, and therefore I will just state it in a different way without proving it, by giving it as an exercise. Therefore, this is an exercise. Suppose you have a sequence A of integers, and then count how many such elements are there up to x. In this sequence, count how many elements are there up to x, and suppose this number is bigger than, let us say, 1 over 10 times x over log x. Therefore, you have a sequence of integers, count how many of them are up to x, and suppose the number is 1 over 10 times x over log x.
For
every x. Then the reciprocal of the sequence diverges. On the other hand, if you have another sequence which is b1, b2, etc., b3, and you know that the number of elements up to x is less than some 10 times x over log square x, and then if you look at that reciprocal, and that reciprocal is convergent. If it has around x over log x elements, the reciprocal diverges, and if it x over log square x elements, the reciprocal converges.
What is special about 10?
Any constant. The log and log square is very important, because log power 1 plus epsilon itself, it is convergent. At log it is divergent. At log x power 1.01 it is divergent, convergent already. And therefore he stated the result that the twin primes behave differently from primes, because there are a number of primes is at least 1 over 10 times x over log x, and therefore the reciprocals of the primes converges, whereas the twin primes he put x over log square x, and therefore the reciprocal diverges. Is it okay? Now I want to write this Bruns result in a slightly different way. I want to write the Bruns result in a slightly different way, and therefore now I am interested in the number of primes, for example, and therefore this is number is equal to the number of elements which are co-prime to P z 1. How many elements are there which I have no common factor up to less than z. This number I can also write as summation over A, omega A, where omega A has the property that omega A is equal to 1 if A and P z are co-prime, and omega A is greater than or equal to 0 if A and P z are not co-prime. Therefore, I put a weight. The weight is 1 if A and P z are co-prime, and the weight is non-negative if A and P z are not co-prime. Originally, Eratosthenes chose the weight which is summation d dividing n, d divides A, d divides P z mu of d, which is exactly 1 if they are co-prime and exactly 0 if it is not co-prime. But on the other hand, Bruns came up with an idea that you don't take all of them, you take only part of the d, and when you take the part of the d, if it is 1 if they are co-prime, and if it is non-negative it is not co-prime. Good. And once you give this much, then the next step by Selberg is almost obvious. What do I need? I need a number which is 1 if it is something happens, and if it is 0 greater than or equal to 0 if that something doesn't happen. And hopefully it should have a lot of parameters so that I can also play around. And I can choose the parameter to optimize various things.
But greater than or equal to 0, it should not be allowed to take large values.
Very large values. Okay? And now what Selberg did was simply the following. Yeah, what Selberg did is simply the following. You choose your real numbers lambda d, arbitrary real numbers lambda d, with lambda 1 equal to 1, and all other lambda d is arbitrary, and my weight omega a is summation t dividing a, t dividing p of z, lambda d whole square. Now let us see what happens. This is summation d dividing a, d dividing p z lambda d whole square. If a and p z are co-prime, then there is only one value of d, because d divides a, d divides p z, and therefore only one value d equal to 1 alone survives, and that is lambda 1, and therefore in that case the value is 1. In the any other case, it is a sum square, and therefore it is non-negative. I don't need to carry. Which essentially means now you have a sieve methods where you have various parameters lambda 2, lambda 3, lambda 4, etc. all at your disposal. And then you can optimize it in such a way that everything works. And this really turned out to be much better than what Bruce did. And that is the Selberg. Therefore, it is summation d dividing n lambda d whole square, and that is the weight, and then you can do that, and then you can do the same thing, and instead of that you can replace it by that. Okay. Therefore, this condition a and p z co-prime can be always replaced by summation lambda d whole square, and then you can simplify. And then you can have a main term and you can have an error term, and then finally there will be a main term which is summation lambda d1 lambda d2 by the LCM of d1 d2, and there will be an error term, and we will assume that the main term will dominate, the error terms will be negligible, and then you choose your lambda d1 lambda d2 in such a way that this main term will be optimized. Okay, and that either you can do it by Lagrange multipliers, summation of squares, various methods, and he computed what lambda d is, and that is that. What are the various things which one can do by this? Instead of this one, he suggested that instead of this one-dimensional sieve, one can do the two-dimensional sieve, which turned out to be very important, and therefore let me see. We can prove something called the Brun-Tishman's theorem, which counts the number of primes in an arithmetic progression congruent to A modulo Q, and you can get an upper bound for it, again by Brun sieve. Therefore, you can actually count how many primes are there in an arithmetic progression. And then he suggested a method for twin prime problem, which was supposed to be the main part of my lectures, and lack of time that whatever I am supposed to give the main part, let me skip. And that's the main part of the lecture. And the most important thing is this, that when you take two consecutive primes, their difference, you see on the average log Pn, because the number of primes up to x is x by log x, therefore the average difference will be around log. But now what it proves is that if lim-inf is actually 0, which means there are infinitely many times when the difference is much smaller than little o. Okay, and that was the theorem, and then afterwards it was improved much better by Zhang, who proved that there are infinitely often the difference of two consecutive primes is at most 10 power 70, which is rather surprising because your average difference, which is log n, goes to infinity, and therefore for infinitely often a bounded difference is something surprising.
Why are you choosing m instead of m plus 1 hm? hm instead of
H1 it should be.
Yeah, it should
Yeah.
Just H1.
Exactly. H1 is what we are talking about. Yes. Yeah. But in general, you can do it for HM. When you take m consecutive primes, how much can be the difference? And this number was subsequently reduced to 4,280 by the Polymath project. I mean, I don't know whether you have heard about the Polymath project. Probably, if you have not heard it, that's better. You know better that how a joint work would always be helpful in really getting all the implements cleared and would be able to prove the things. And yeah, that's all. With that, I will. Thank you.